Okay, so we'll proceed with the second talk of the afternoon session. So let me introduce, with a pleasure, one of the young superstars in the subject, Kevin Costello, who's going to tell us about mirror symmetry in fact. Kevin?
Thanks for getting yeah, and I'd like to thank the organisers for what's been a very, very enjoyable conference, and I've learned a lot. So what I'm going to be talking about is, well, non-homological, like preconceived mirror symmetry. So how, back in the 90s, you wanted to relate Gromov-Witten invariance to something called the closed string B model. So I'll be introducing, describing some work I did with C. Lee, who is not here. I think he had to go back to Harvard, where we analyzed this BCOV quantum field theory. These guys proposed an approach to the B model in the mid-90s. They said it was some quantum field theory in the Calabi-Yau. So we construct this quantum field theory in some examples. And then C has proven that indeed mirror symmetry holds for the elliptic curve. So that you can figure out the Gromov-Witten invariance of the mirror elliptic curve from this quantum field theory elliptic curve. Okay, so I hopefully won't go too slow, but I'll start pretty slow. So if you remember back in the day, before Kontsevich came around and told us what we should be doing, the idea was there was this weird relationship between numbers of rational curves on X and variations of Hodge structure on the mirror. Now, this doesn't make any sense a priori because, one side we have this collection of numbers, on the other side we have this, algebraic structure. So we'd like to put both sides, make them both be examples of the same kind of thing, which we can then compare. So one very nice way to do this was proposed by Giventhal and Baranikov. Possibly, I'm not sure, there were probably antecedents of their ideas, but they said that we should encode both sides as a symplectic vector space with a conic Lagrangian submanifold. And then mirror symmetry is a statement the two symplectic vector spaces, conic Lagrangians, match up. Okay, so I should tell you what these, in the A and the B model, what is the symplectic vector space and what is the Lagrangian. So from this point of view, the B model is much easier to write down. So, well, okay. I'll start with the simplest one. If you're familiar, as Paul mentioned in quantum cohomology, there's big and small quantum cohomology, descendants and so on, and various extra pieces. But the simplest one for the B model, you just take our symplectic vector space to be H3, Calabi-Yau threefold. And while the Lagrangian submanifold is, I consider this moduli space of possible deformations of my Calabi-Yau, but deformations as a Calabi-Yau equipped with the holomorphic volume form. And you observe there's a natural map from this moduli space to H3 just by taking my deformation and looking at the cohomology class of the corresponding holomorphic volume form. Now, we define our Lagrangian submanifold to be the image of this map. So now we have H3, and as you can see, it's clearly conic because I can rescale the volume form. So it's conic, and it's kind of formal, defined near the fundamental class, or sorry, the cohomology class of the volume form in X. So we have this formal Lagrangian cone, and this encodes everything about the genus 0B model. Okay, so what happens in the A model? So what Giventhal says to do is, well, H3 under mirror symmetry corresponds to the direct sum of the PP cohomologies of the mirror. So the obvious symplectic pairing on H3 corresponds to just a very simple symplectic pairing you put down on this direct sum of the cohomologies. And you observe in this case, well, let's see, what am I getting to? So we're going to construct a Lagrangian cone from the Gromov-Witten invariance. So we have this symplectic vector space. Now, as usual, we should arrange our Gromov-Witten invariance into some kind of generating function. But here, we're only interested in small quantum cohomology with no descendants or anything like that. So we just look at the Gromov-Witten invariance as a function on H00 and H11. And we just arrange them into a power series in the usual way. Okay. Now we observe our symplectic vector space is the cotangent bundle to H00 and H11. So the Lagrangian submanifold, I just take the graph of the differential of this generating function, and I view it as a Lagrangian submanifold defined near the point 1. Okay, so what's really nice, Kiventhal showed, is that the axioms, the string equation, the dilaton equation, various other properties of Gromov-Witten invariance precisely say this is a Lagrangian cone. All the axioms can be phrased in terms of geometry. Okay, so this is the basic situation. If you'd like to generalize a little bit, the story I want to talk about includes descendants. Oh, actually, there's one. I'm sorry, I keep forgetting what's on the next slide. So, of course, mirror symmetry says the two symplectic vector spaces and the two cones should match up. So we should try and match various structures. Of course, in the A model, we have to take this Q, this Novikov parameter, because we can't sum over Gromov-Witten invariance of all degrees. So to get that Q appearing in the B model, we need to take a family of varieties over some formal puncture disk. Okay, and as we saw in the A model, we didn't just have a symplectic vector space, it was polarized. There was some canonical polarization. And this canonical polarization allows us to translate between the cone and the generating function. If I have a polarization, the generating function is uniquely determined by the cone. But in the B model, this is a quite subtle issue. There is no natural polarization. What you do have is 1/2 of a polarization. You just take F2 of H3. So in other words, H21 plus H30 inside of H3. This is a Lagrangian submanifold. And this is nice because, as we know from the classic days of Hodge theory, this submanifold varies holomorphically as I vary x. Now, the naive guess is to choose the complex conjugate to be our splitting. But that's not right for various reasons. One of them is that this complex conjugate doesn't vary holomorphically, the famous holomorphic anomaly equation. So the correct thing to do is you analyze the monodromy around this large complex structure point to get the other polarization. Okay. So this is the story without descendants. Actually, I should get out my clock. So let's put descendants into the picture. So if you recall, Gromov-Witten invariants with descendants are defined to be integrals over the moduli space of stable maps, the usual story. But we put in these cohomology classes, psi I, which are first Chern classes of canonical line bundles on the moduli space. So I assume this is quite familiar to most people, so I won't go over it. And as usual, we can construct a generating function from these guys. So we're going to arrange things so that the generating function is a function. I'm an algebraic geometer, so curly O means functions. It used to be an algebraic geometer. It's a function on this space, the cohomology adjoin a formal parameter. And we define it so its Taylor expansion is these descendant invariants. Okay, so how are we're going to use this to construct an infinite dimensional Lagrangian cone encoding this theory with descendants. So it's going to live in some infinite dimensional symplectic vector space, namely the cohomology of x adjoins some parameter t. I have a feeling I'm going too fast. So we take the cohomology of x adjoin a parameter t, and given tall tells us there's a very natural symplectic pairing. I don't know where you came up with this, but it turns out to be the exactly right thing to do. And yeah, that's our big symplectic vector space. Now, of course, this is the cotangent bundle on the part with no negative powers of t. And we saw that the generating function for Gromov-Witten invariance was a function on that space, no negative powers of t. So we define our large Lagrangian cone, the A model version, to be, as before, just the graph of this. Oh, yeah. So this is, Given Delta doll is really beautiful work in the 90s, and I think people don't it's been forgotten a little bit, I think, by people who don't work in Gromov-Witten invariance. But the beautiful thing is that so the axioms of Gromov-Witten invariance are precisely saying that this guy is conic and preserved by the operator multiplying by t. That's the string equation, says it's preserved by the operator multiplying by t. Or sorry, the Dilaton equation. Okay. So let's think about, I'm going to write down the mirror version. So the A model, we just defined it in terms of the graph of this functional. But the B model is something much more geometric. It's very naturally seen as a cone. So in the B model, it's going to be built from polyvector fields, because the natural way relationship between the A and the B model is cohomology, and the A model becomes polyvector fields of the B model. So this is, again, some story which I hope is pretty familiar. Define the ij polyvector fields to be as above. We can identify with forms using the choice of holomorphic volume form. So when we can have these operators d bar and partial, I don't know, d, which come from the usual two operators on the space of forms. Now, you might say, well, why don't we use forms? Well, the reason is polyvector fields is a natural commutative product just given by wedging them. And that differs from the one on forms. So this is the natural thing to do in the B model. And there's a trace where we just take our polyvector field, contract it with the volume form, and then integrate it. This makes these polyvector fields into some kind of Frobenius algebra with these two operators, d and d bar. Okay, so what's the Lagrangian cone? Well, the symplectic vector space, I'm going to write this down for posterity, because I'm going to be referring to it throughout. The symplectic vector space is polyvector fields in X, adjoin some parameter, and it has a natural symplectic pairing. And for those in the know, the differential we give in it, some kind of Tate differential, something which appeared in Anatoly's talk. You saw that. And the Lagrangian cone is something very simple to write down. It's just the set of things of the form t e to the f over t, where f has no negative powers of t in it. And as we see, this is a formal germ of a cone defined near the point 1, because I think of f as being near 0. Yeah?
Trace is a symmetry or C-symmetry?
The trace is... Oh, I think I forgot to include a shift by the dimension of x, which makes this symplectic. Okay, so that the trace is symmetric, but once you include the correct shift, this becomes a symplectic pairing. Maybe I didn't, but anyway, this is certainly symplectic. Okay, so you might ask, what did this have to do with what we saw before, where I said the Lagrangian cone is the moduli of deformations? Well, this is also the moduli of deformations, but it's the moduli of kind of extended deformations. Where, you know, people talked a lot about the extended moduli space of Calabi-Yau's again back in the early days of mirror symmetry. So let me explain why we should think of this cone as being moduli of extended deformations. If I have some element in this cone, this is some kind of, you know, DG manifold, so the only elements we really kind of know about are those which are closed. So if I have some element which is closed, this happens only if this F in here satisfies the master equation, a certain Mark-Cartan equation. And this is the Mark-Cartan equation which allows us to deform our Calabi-Yau. And so, for example, if F is an element of omega 0, 1, the tangent bundle, this Mark-Cartan equation precisely tells you we have some family of Calabi-Yaus going in the direction given by F. And if F is in some other, you know, exterior powers or whatever, we should think of that as being some kind of derived moduli space, extended moduli space. And a more formal way to see this is that I can think of deformations of my category. That's controlled by Hochschild, or say, cyclic cohomology, and this space is isomorphic to cyclic cohomology. Oh, okay. So there are some fun things you can check. That this is preserved by the differential. Well, clearly it's clearly a cone, because I can multiply this by some constant, and I can change F. And it's also clearly preserved by multiplication by T, because I can add something involving T to F. Still preserved still in there. So these are precisely the properties Giventhal says are required to produce for you a Frobenius manifold. So from this point of view, I mean, that's why I like this. It's completely obvious. Just write this thing down, and it's the B model Frobenius manifold. Okay. Okay, so now, of course, the mirror symmetry conjecture says the A and the B models coincide. There's some isomorphic, or in this case, quasi-isomorphic, because we're taking DG symplectic vector spaces. Quasi-isomorphism of symplectic vector spaces from the A and the B models, which takes one Lagrangian cone to the other. And, you know, Giventhal, Liang, Yu Yao proved more kind of classic standard formulations of mirror symmetry. And Barannikov's work, I think, allows you to, he did a lot of work on proving mirror symmetry with descendants, which will give you this result in many cases. And did I say that this, yeah, this Lagrangian cone was invented by Barannikov in some other way. He didn't want it quite like this, but. Okay, so now we see that the genus 0 A and B models, both sides we have this Lagrangian submanifold. So you want to ask what goes on at higher genus. Well, the natural guess is that we should try and quantize this picture. So the symplectic vector space, as usual, we can quantize it to give a Weil algebra. And in this story, a Lagrangian submanifold will quantize to a vector in the Fock space. This is some standard deformation quantization story. So let's see how this works for the A model. And there it's very simple. The Gromov-Witten invariance will give us the desired state in the Fock space. So our A model symplectic vector space, see, it's the cohomology of X adjoined Laurent series, but I can think of it as the cotangent bundle to the cohomology of X adjoined Power series. Since it's the cotangent bundle of something, I can identify the Fock space of this symplectic vector space with just the algebra of functions in these cohomology value power series. Now we have the generating function for Gromov-Witten invariance is an element of this guy. So I can just take the exponential of that to be the A model partition function, and it's a vector in the Fock space as desired. And pretty much by definition, as h bar goes to 0, this converges on the Lagrangian cone we wrote down earlier. Okay. So the B model is what I'm going to talk about, obviously much more interesting. So if you remember, there was two stories, and both on the board. So the small story where we only see h3 of x, and this kind of larger story involving descendants where we see all polyvector fields. So in both cases, we should expect that the partition function should be a state in the Fock space for this symplectic vector space. So in some sense, what are we doing? In both cases, the Lagrangian cone is the moduli of Calabi-Yau's. So this is some kind of quantization of the moduli of Calabi-Yau's we're looking for. Okay, so let's do an interesting problem. How do we quantize this guy? And so the aim, what I'd like to explain, is how you can do this in some cases using quantum field theory. Okay. So let's look at the small version first, where we're quantizing the classical moduli space of Calabi-Yau's. This was studied by Brzezinski, Scotti, Uguri, and Baffa in 1994. So what they say is we should consider some theory of complex gravity on X, right? I mean, we know the classical theory is about the moduli of Calabi-Yau's. So I suppose the guess was that the quantum theory should be some kind of gravitational version of that. So the fields of that theory include deformations of complex structure. The gauge group is a diffeomorphism group. This classical solutions is the moduli of Calabi-Yau's. And they say the partition function of this guy should be the B model partition function. Now, shortly after, Witten argued that we should really think of the thing BCOV constructed as indeed a state in the Fock space for H3. So this is our starting point. But we'd like to do this with the infinite dimensional Lagrangian cone, which I've written down here, where we try to quantize this submanifold, the space of all polyvector fields. Okay. So we're going to do this by writing down some extension of the BCOV theory, which will have more fields to include the descendant invariants. Okay, so how do we do this? Well, we just say we have this Lagrangian submanifold, so we can identify the polyvector fields with the cotangent bundle, as before, of the polyvector fields with just positive powers of t. And we'll take those guys to be the fields of our theory. And I hope this will be clear why we're doing this shortly. And now the Lagrangian submanifold, well, it's the graph of a function on our space of fields. So this function is the action functional we're going to use to try to quantize the theory. Okay, so actually this is strange. I mean, the two senses of the word Lagrangian are coinciding, right? So you might ask, this seems a little strange. I'm writing down this t to the f over t. How do I consider that as an action function for quantum field theory? Well, you can compute the function whose graph is this. And the answer, somewhat surprisingly, involves integrals over moduli spaces, which kind of suggests we're on the right track. This is just some computation. Basically, both sides satisfy the string and dilaton equations, therefore they must be and we're going to use this basically as the action function for our quantum field theory. Okay, but now you might notice something funny, right? That we're integrating over these moduli spaces. M bar 0n is, only makes sense when n is at least 3. So this function f0 is cubic. Well, the leading term is just the trace of product of 3 Pauli vector fields plus then this higher order stuff. So it seems a bit strange to try and consider quantum field theory where the action functional doesn't have a quadratic part. But that's okay. I mean, this is a very weird quantum field theory. And in fact, a similar problem appeared in the original paper, ECOV. So it turns out that you can make perfect sense of the action functional. The reason is, so you can make perfect sense of, with this quantum field theory. You can try to quantize it, but it's just some degenerate kind of field theory. One way I like to think about it is in the BV formalism. Classical field theory is the same thing as a symplectic manifold with some differential of degree -1. Now, in that story, the action functional S is determined from the differential by saying the action functional is the Hamiltonian vector field for this differential. And the differential is some vector field in my symplectic manifold. Now, here we're in a Poisson situation, and I do have a natural differential. The linear term of the differential is that. Should I write this down right? I think I didn't write this. I think I said something not quite right here. But the point is, this is an entirely analogous situation, except that we're replacing symplectic story in usual B formalism with a Poisson story. Yeah, so we can try and proceed and apply the usual Feynman graphs. Whatever, it all makes sense here. So let's not worry about that. Okay. So I mentioned the BV formalism. And to have a good theory in the BV formalism, you want to have something called the classical master equation, which is this equation here. Q is the differential on whatever space of functionals, and I want Q phi plus phi brackets phi equals 0. Now, there's some nice dictionary between these Lagrangian submanifolds and classical master equation, is that if I take a function, then this functional satisfies the master equation if and only if its graph is a Lagrangian preserved by the differential. Okay. Now, since we defined our action functional to be the functional whose graph is this.
It's just a differential you wrote on the previous page, or is Q a new symbol?
I think Q meant this symbol.
That thing.
D bar plus D delta, yes. It's the linearized version of the differential. Okay. Yeah, so we defined F0 so that its graph was this Lagrangian submanifold, this T to the F over T thing. This is preserved by the differential, so therefore F0 satisfies the classical master equation. So you have this dictionary. You can interpret this function in two ways. It's classical action functional for field theory, or generating functional for Lagrangian. And the classical master equation means something in both settings. In the field theory, it means some classical consistency for a gauge theory. Our action is invariant out of the gauge group. On the other side, it means we have Lagrangian submanifold preserved by the differential. Okay. So our aim is now to quantize classical field theory defined by this. And we're going to use I developed some techniques for renormalization, which we'll apply here to construct the quantization. So the first thing you might think of, like the most naive idea, is what does it mean to quantize? Well, there's something called the quantum master equation, which is supposed to be it's the classical one plus this h bar delta term. That's supposed to be a consistency condition for a quantum gauge theory. And we might look for a solution of that equation. And again, you can argue, this is a little formal, I'll explain why in a second, you can argue that this is two interpretations. One is that our quantum gauge theory is consistent. And the second is, well, I should explain this a little maybe. The second is that our functional defines a state in the Fock space preserved by the differential. So, why, you might ask, what has this delta got to do with the Fock space? Well, the answer is our symplectic vector space is a sum of two pieces. The positive part and the negative part. And the differential is d bar plus t delta thing. So now if you see, the differential has a cross term mapping the negative part to the positive part. So this polarization is not preserved by the differential. Let's call this Q. So therefore, if I consider the operator on the Fock space, I should quantize this linear symplectic morphism to an operator in the Fock space. Q hat acts on the Fock space. And you find that Q hat is the usual differential plus h bar times the BV operator. Actually, it turns out the BV operator can always be interpreted in a way like this. So that's why you have something like this. OK, so why is this naive and why is this problematic? Well, everything written on this page is kind of nonsense because this operator is not defined. Now, for me, the fact that this operator is not defined is really one of the key problems of quantum field theory. This is, any time you try to understand quantum field theory or write one down, you're going to run into the problem of ultraviolet divergences. And in the approach I'm using, precisely here that ultraviolet divergences appear. So there's a solution to this problem. So this is the stuff I did in normalization. It allows you to make sense of this operator. And I want to, no, I'm going too slow. How long do I have left, Livno? OK. So there's some definition. This is going to fly by pretty quickly, so let's not worry too much about it. So we can make sense of this BV operator by saying, we can ask for a family of effective actions, one at every scale, and I can ask that my effective action satisfies the quantum master equation with some effective BV Laplacian. Now, this effective guy involves mollifying out. The original operator delta was not defined because it was some distribution supported on the diagonal. Now we're mollifying it, and now it makes sense. So I can ask for a family of solutions, one for every L, related by the normalization group equation and satisfying the quantum master equation. And of course, we'd like this to be local as L goes to 0. OK, so this is a little technical. So we have some definition of quantization. We won't be able to absorb it right now, but we're going to try and use it in our context. OK. So the way I set this stuff about normalization up is that if you want to quantize some field theory, you never actually really need to play with the Feynman diagrams and construct counterterms by hand. You just calculate the obstruction groups for quantization. And if they're 0, you're good. If they're not, you're in trouble. But what my collaborator Celie and I have showed is that on any complex torus, we construct a quantization kind of canonically. I should say, this should really say a complex torus equipped with a trivialization of the tangent space at the base point. And the proof is just some obstruction theory calculation. Now, yeah, in higher dimensions, it's not quite as the results aren't quite as strong as we'd like. There's some like finite dimensional. We choose one nice quantization, but there's some finite amount of ambiguity. But on the elliptic curve, everything works as nicely as you could hope. Okay, and in this case, okay, so now suppose we have our quantization. Well, we saw that the quantum master equation says that something in the Fock space is closed because the quantized differential involves the EV operator. This continues to hold in our framework with effective field theory. So once we have our quantization, I can just take the cohomology class in the Fock space and think of this as a partition function of our theory. Okay. I'll say a little bit, I mean, you may think this is very strange and that the Gromov-Witten invariance, you have a bunch of numbers, and here we have a state in the Fock space. You can turn this guy into a bunch of numbers if you choose a polarization of this symplectic vector space. I say how to do that in a little bit. Okay, so yeah, the cool thing that C proved is that mirror symmetry holds for the elliptic curve in this context. So here we have our two symplectic vector spaces. One is just the cohomology of the A model elliptic curve. The other one is this polyvector fields of the B model elliptic curve, and both of them involve Laurent series. And there's some very simple way to identify them both, one with the other. And what happens is, well, we saw the A model partition function was the generating function of Gromov-Witten invariance, and this becomes precisely this state in the Fock space. Okay, so I think in the last few minutes, do I have a few minutes left now? Last few minutes, I'd like to say a little bit about how we prove this. Okay. So actually, before I do that, I should say a little bit about how we turn this, how we match this approach to the B model up with the usual things people do in the A model. Well, as I said, if we want to get some numbers, if we want to turn a state in the Fock space into some kind of sequence of numbers, we need to choose a polarization of our symplectic vector space. And in this context, this symplectic vector space was really defined using, it's just built from the cohomology. So to choose a splitting of the Hodge filtration, that will give us such a polarization. So if I choose some S inside of H1 of E, which is a complementary subspace to the space of holomorphic one forms, then I get these B model correlators from my state in the Fock space. They depend, just like Gromov-Witten invariance, on some polyvector fields and on some powers of T. And the powers of T I should interpret as descendants. Okay, these are nice. They depend as nicely as possible as you could ask for on the elliptic curve and on S, holomorphically on E, holomorphically on S as well, and SL2Z invariant. And in addition, if I change S, these guys change in some controlled way because there's some Bogly-Abuev transformation which controls the change. Now, if you're naive, you might think, well, I mean, maybe a very natural thing to do would be to take the complex conjugate splitting of the Hodge filtration. And this does not vary holomorphically with E. And that leads to the fact that if I use this splitting, I get something which is not holomorphic, the so-called holomorphic anomaly equation. I mean, but the failure to be holomorphic is kind of controlled by these Bogly-Abuev transformations I mentioned. Now, the correct splitting to use is the one corresponding to the large complex structure limit. So, if we have the elliptic curve with modulus tau, then I can consider the Hodge filtration F1 for the modulus sigma. In other words, I can consider those one forms on E, which are holomorphic with this complex structure. And then the complex conjugate to that guy, like the one forms on E, which are anti-holomorphic with respect to this complex structure sigma, is a complementary subspace for the Hodge filtration on E. Now, the correct thing to do, it turns out, is that to match up with the A model, we take some sigma in the upper half plane and send it off to I infinity. The limiting splitting exists. And we get this kind of splitting of the Hodge filtration. And if you read BCOV, they say this is what they mean when they say fix tau and let tau bar go to infinity. And now once we've done this, once I've sent everything off to infinity, you see that things are still holomorphic in tau. Well, the dependence on sigma is gone because that's gone to infinity, but I've broken the SO2Z invariance. So these are no longer modular. They're holomorphic but not modular. So they're quasi-modular forms. They involve E2. What C, my collaborator, proves is that these coincide with the actual Gromov-Witten invariance of the mirror curve. In some really simple way, you just match up polyvector fields with cohomology classes in the most obvious way you can do, and they're the same. Okay, do I have time to go more?
Yeah,
Okay, so let me try and sketch it a little bit. I mean, C is not here. I can embarrass him. His proof is a real tour de force. It's surprisingly hard result, and yeah, it's very impressive. So the first thing we do is, well, Akunkov and Pandey calculated the Gromov-Witten invariance of an elliptic curve. And the key step was to prove the Virasoro constraints. So we also proved the Virasoro constraints hold in our context. And we do this by obstruction theory, which is, well, classically, we have a formula for everything. It's kind of obvious they hold. We know there's unique quantization. Because the quantization is unique, any symmetry of the classical theory extends to a symmetry of the quantum theory. Therefore, they hold at the quantum level. Now, the Virasoro constraints means that you can remove from the correlators you're trying to calculate everything except stuff involving this class in H1 of the tangent bundle. But this is the mirror to the fundamental class of a point in the A model. It's what Akunkov and Pandey call the stationary sector. Okay. Now, maybe here's the absolutely key idea. I'll draw my elliptic curve. I'm taking some limiting splitting of the Hodge filtration. I'm taking this guy in. This is really a class in H1 structure sheaf, if you like, and in some limiting splitting of the Hodge filtration, when I represent it as a de Rham cohomology class, it becomes supported entirely on the A cycle. So if I take n of them, I can make them all supported on n parallel A cycles. Now, this means when we do our computation, we have this kind of effective action we're trying to compute built by Feynman diagrams. It means that we're going to have one vertex on every one of these circles connected by some lines. And the propagator is the Weierstrass P function. Now, if you think about formula like this, you'll see this is exactly the same formula as you might find if you calculated the expectation values of operators in the free boson vertex algebra. Okay, so now we find there exist operators in the free boson whose expectation value is what we want to compute. Okay, now let's look at the right-hand side of this equation. It's obviously symmetric under permutation of the ki's. Well, with these operators, it's not obviously symmetric. Well, we deduce from this that these operators must commute. Okay? So now we have this infinite family of commuting operators in the free boson, so it's a completely integral system. And there aren't very many of those. It's completely determined. This is some quantum W algebra. It's completely determined by its classical behavior. I can figure out there's a unique way to turn these classical things to Poisson commute into this series which actually commute. Now, C says, at this stage, we apply the boson fermion correspondence. They become some commuting operators in a system of two free fermions. And now, you read Akunkov and Pandey's paper, what they say the A model correlators are their expectation values of commuting operators in two free fermions. Now, we just have to match up these operators with these. Well, they all commute, so there's kind of no freedom. They pretty much have to be the same. And that completes the proof. Yeah, I think I'll stop there. Thank you.
Any questions?
So how does quantization work?
In what sense? What do you mean? How does the quantization work?
You said the zero is just for this context.
Yes. So you're asking, why do we have that restriction? Okay, so what? Okay, so our construction is a little broke. So we have to calculate the abstraction and deformation groups. Quantization show there is this unique quantization. So what we show is that there's a version of the PCOB theory which works on a caveat with an anticanonical divisor, some logarithmic volume form. So we show that the log PCOB theory kind of exists and is unique, quantizes uniquely everywhere. And from there, we can restrict the complement of these and put in any complex force. Now, that's why it's a little unsatisfactory in higher dimensions, but in dimension 1, n equals 1 on C, or elliptic curve, there exists unique quantization. So in higher dimensions, there's possibly some finite ambiguity in the quantization, but if we make it compatible with the log BCB theory, it's unique.
Other questions? Young Bin?
Well, no, of course, for us, the complex torus will have trivial Gromov linearity in high dimension.
Yeah.
So I really hope you can do other target as well. Huh?
Me too. It's very close to your talk. I don't really mind to say this all along, but you can do the same thing for the if you have a superpotential. We haven't really developed in detail, but there's a very similar story with the superpotential. The Lagrangian cone is just I just move everything over by my superpotential. And as you see, this Lagrangian cone is precisely the space that Eva was talking about this morning. Space parameter space for the algorithmic theory. Anyway, we can quantize this one too. So that links to the theories you were talking about in your talk. Hopefully we can it'd be nice if we could show them the same as what you were doing.
I'm sure that's it.
Yeah.
Andre?
So, did I understand correctly that knowing that there's a unique quantization that implies that knowing the genus 0 potential that completely determines the higher genus?
No, quite. I mean, if you think of the axioms for quantization, it's not just saying the state in this Fock space. It's also saying that the state in the Fock space is local. It comes from some kind of local quantum field theory, and that's much stronger than knowing just the Lagrangian cone. So, makes sense. I mean, if I just take the cohomology of everything and look at the genus 0 Lagrangian cone, that has loads of different quantizations. But there's only one of them which is local. In a sense.
Right, but what extra, I mean, so you're saying that there are different versions of, so is there more than one possible quantization of this like classical Lagrangian cone?
If you just took the cohomology of everything, yes. If this classical Lagrangian submanifold on page 3, well, of course, you can just write down anything. But if you want it to be given in terms of local things on your clavier, that's a very strong constraint. So that's the really key point.
Other questions? No, let's thank Kevin.